So let's take a look at the last type of layer 2 protocol. Let's call CSMA, carrier sense multiple access. Okay, we already know what is multiple access, but what is carrier sense? Carrier sense means listen before transmit. Carrier sense means you have to sense the channel before you send. So if the channel sensed idle, then you can send the entire frame. But if the channel sensed busy, then you don't have to send the frame out to interfere the other signal, right? So you defer your transmission. So that is what we call carrier sense under multiple access environment. Okay, and in this hour we'll talk about CSMA. CD is one of the version of CSMA. Okay, CD stands for collision detection. Okay, we'll talk about this later. Okay, let's first take a look at carrier sense, CSMA's carrier sense. Okay, so right here we have 4 nodes A, B, C, D, and we notice that I write it right here. Spatial layout of node. That means in a line, in an environment, A, B, C, D are actually, B is between A and C, C is between B and D, and A and D are far away from each other. That's what we call the actual spatial layout of node. Because when we talk about CSMA, the position, the layout of each node is very, very important. Okay? So we can see the spatial layout of nodes and the time right here. Also time right here. So time goes by. So at this moment, okay, at time 0, B wants to send a frame out. Okay, and as we mentioned before, we use carrier sense, right? So if channel sense idle, it transmits the entire frame immediately. So B sends the channel and A, C, D do not send any signal. So B will send out its first bit. Out. And as we mentioned before, because we have in network, we have propagation delay, we have transmission delay, right? So this first bit will propagate in this spatial layout from B to A and from B to C to D. And because the spatial layout of this node, okay, A, okay, you can simply just draw a line right here to represent the position of A. Okay, so for A, it takes this small amount of time to get the signal sent from B, because the signal needs some time to propagate from B to A. So let's take a look at this one, D. Okay, it takes that amount of time to transmit, to propagate the first bit from B and to C and then to D. So for D, it here, okay, it can sense the signal right here. Okay, so after that, okay, B will continue send its second bit, its third bit, so on so forth, so on so forth. Okay, so at this moment, that is B's last bit, and it will be propagate to the environment like here. So you can see that the yellow parts are the signal transmit by B, and it will propagate to A and to C and to D. And you can see that because of the propagation delay and the distance between different nodes, the time, the exact time that C receive the signal and D receive the signal are different, right? Because they have different distance to B. Okay, so you know that is how signal are propagated by B. But take a look at this one. Okay, right here at T1, if D want to send a frame out. So as we mentioned before, because it is carrier sense multiple access, so at T1, D sends the channel. But you have to know that at T1, the first bit sent by B, that signal has not arrived D yet, right? So at this T1 moment, when D sends the channel, it is empty. So at this time, D will send its first bit out. And so on and so forth, so on and so forth. And that is the last bit sent by D. So you can see that in this figure, the red parts are the signal sent from D and propagate to C, B, and A. Okay? So you can see that even if those nodes, indeed, they do carry sense, but because of propagation delay, sometimes D cannot sense. B has already sent certain signal out, so D will send its signal out, right? So let's take a look at A, okay? A will receive B signal, but at this moment, it will receive B signal and D's signal. So in this part, okay, the red signal and the yellow signal overlapped it, so A sends collision. Okay, and again, if you take a look at C, okay, you draw a line for C. C will sense the collision right here. And of course, B and D will sense the collision as well. So that means even if you apply carrier sense mechanism, due to propagation delay, it is still possible that those nodes will have collision. Okay, so CSMA is not is not the best thing you can do. It's not the best layer 2 protocol because it is still cause collision. Okay, propagation delay is the major reason that they still have collision. Okay, so the next part is CSMA CD. CD stands for collision detection. So right here, you simply take a look at this small time. Okay, that means when you sense the collision, for example, for B, when you sense a collision, you can simply just abort your transmission because the signal is overlapped. So the receiver is not possible to receive the correct signal. So you don't have to send the rest of the frames out. You can simply just abort your transmission. Okay, so it's right here. For D, okay, when it senses the collision, it takes some time to stop its transmission. Okay, so after collision detected, okay, they abort the transmission, and after that they will wait the channel to be empty, to be idle, and then B and D will try to find out some other mechanism to decide who can transmit after this collision. Okay, we will introduce it later. Okay, so CSMA CD reduced the amount of time wasted in collision because the transmission aborted on collision detection. Okay, it's quite simple, right? So let's take a look. What if they sense the collision, and how do they recover from such kind of collision? Okay, so right here we have the actual Ethernet CSMA CD algorithm. Okay, we have 5 steps right here. So follow me. Okay. Actually, it's quite simple. Okay, the first step, the interface card receive diagram from the network layer and create a frame. Okay, that is easy one. Okay, So if the network interface card sends channel, okay, we have two different situations. 2.1, if the channel is idle and then the network interface card start to do transmission. Okay, so let's directly go to step number 3. If the network interface card transmit the entire frame without collision and the network the card is done with frame, that is the most ideal way. Okay, step number 1, you get the diagram and create the frame. Step number 2, you sense the channel. If it's idle, then just simply send the frame. And number 3, if when you send the frame, you hear no collision, and that's done. So that is the ideal way to send the packet. Okay, but sometimes, okay, step 2.2, when you sense the channel, if the channel is busy, that means somebody else is transmitting a frame. So you wait until the channel idle. Once the channel is idle, and then you transmit the packet, the frame. Okay, and it's still the same, right? So if you transmit it, so after channel is idle and you transmit the frame and you send the entire frame without collision, then that's good. That is very nice. Okay, so 1, 2, 3 is very nice, but we have to take a look at number 4, step number 4. When you send your frame and the interface card detect another transmission while sending, that means you encounter a collision and you simply just abort the transmission and you send the jam signal. Okay, so let's take a look at this figure. When you sense a collision, and then you will send a jam signal, okay, to all the other nodes. Okay, it's similar right here. When you sense a collision and you send a jam signal to all the other nodes, so that it guarantees that all the nodes in this subnet knows collision happens. So all the nodes will keep quiet for some time. Okay, so after that, B and D, take this example, B and D will figure out who can send first. Okay, so that is exactly step number 5. So after number 4, the transmission is abort, the jam signal is sent, and then, okay, we have an algorithm called binary backoff or exponential backoff, or sometimes we call it random backoff. Okay, follow me. Okay, so that's right here. N equals 1. After the first collision, these two interfaces, for example, the B and D, okay, choose a K at random from a set. Okay, since it is the first collision, so K is either 0 or 1, right? Because currently M is 1. So that means these two interfaces will roll a die. Okay, that is either 0 or 1. So the network interface card waits K times 212 bits time. So basically it is a time, some second, okay? It is defined in the protocol, okay? It will wait, okay? So for example, B rolls a die and the result is 0. And D also rolls a die and the result is still 0, okay? Then that means both of the network interface card, they wait 0 time and then go back to step number 2. And again, step number 2, they B and D sense the channel and the channel is idle. So they both almost simultaneously send their retransmission out. And as we expect, collision happens again. So it becomes their second collision, right? So the K currently should be 0, 1, 2, 3. You can see that the die has more choices, right? So they have to randomly select a number from 0 to 3. So in this case, maybe both of them roll a die and the number are both 1. That means they have to wait one certain second, right? And then they both goes back to step number 2 and do the transmission again and collision again. That's okay, because when n becomes 3, the K should be like this, 0 to 7. So with more collision, the range of K become larger, right? That means B and D will eventually, with certain probability, okay, they will roll the dice and get different numbers, right? So one of maybe B is lucky, so its number is smaller, so B waits less time than D waits, right? So in such kind of simple mechanism, a random mechanism, they decide who can send first, right? The network interface card who roll a die with smaller number can send first, and the one who has larger number, then it has to wait until the other one send its frame. So it's very simple. We use a random mechanism. So they roll the dice by themselves, they count the weight by themselves, and so on and so forth. So eventually, one of the interface card can send first. Okay? So I think it is a very elegant and smart mechanism, and very simple, because no coordinator, because we don't have a coordinator to decide which interface should send first or which one should send last, because we can simply just use a random use a die to decide such kind of ordering. Okay. So that is CSMA CD. But in this page, it is very difficult to tell you why the efficiency is like that. But we can tell you why it is related to two numbers. Okay, take a look at this figure. Okay, we'd like to analyze the efficiency of CSMA CD. So let's take a look at this one. Because we know the collision is caused by the propagation delay. So if you have a longer propagation delay and you have a more chance to encounter a collision, right? Because you have a longer propagation delay, and that's the thing. If you have a longer propagation delay, you have more chance, right? Because you can send the red signal with a longer time period, right? So right here, if you have a shorter propagation delay, your efficiency is larger, right? Okay. So the other one is if you have a faster transmission rate. If you have a fast transmission rate, that means the height of yellow signal will be shorter. If you have a faster transmission delay and you need less time to transfer a frame, right? So if you have a faster transmission rate, and you will have a less chance to collision, Okay, so right here, if you have a faster, that is larger, right? If you have a larger transmission rate and you have a better efficiency, that means you have less collision. Okay, so you have to make sure you understand why propagation delay and transmission delay is related to the efficiency of CSMA CD. Okay, that's it. That is a CSMA CD. Okay, make sure you understand how random backoff, how binary backoff is used. Okay, and make sure you know why collision still happens when you use carrier sense mechanism, because we have propagation delay. Okay, that is okay. The last topic in this hour, we'd like to talk about the address. Okay, as we mentioned before, in your interface card, we have a 40-bit MAC address burned in the interface ROM. Okay, so usually we write it in this way, something like we use hexadecimal to represent the 48-bit MAC address. So basically, for example, you can simply just take a look at your notebook or your iPad. Okay, you can simply just right here. Did you see that 08 FF44 A0 E0 89? That is the MAC address of my Wi-Fi interface card. Okay, you can simply just figure out what is your MAC address or your interface card. Okay, so basically in a LAN we have IP address, we have a MAC address, and for IP address, the IP address is should have the same net mask and same net ID, right? But for the MAC address, the MAC address is assigned by the manufacturer of this network interface card. So basically, it's just a number. Okay, but IP address, you should follow the rule of subnet. Okay, but for this 48-bit MAC address, we don't have any constraint. Okay, it is because it is assigned by the manufacturer. So MAC address allocation administered by IEEE and manufacturer buys portion of MAC address space to ensure uniqueness, and will set this IP address, this MAC address on each network interface card. Okay. So there's another problem is that how do we when we transmit a packet, a message, okay, at layer 4. Okay, basically, if you want to contact a web server, basically you know it's port number, right? Usually it's port 80, right? And your source port is a random number, right? And at layer 3, if you want to contact again a host, basically you know your own source IP address, and even if you don't know the destination address you want to connect, you can if domain name is used, you can simply just send a DNS query to a DNS server, right? So DNS server will help you to find out what is exactly IP address used by a certain domain, right? So you know the destination IP address. But the other problem right here is when we send a frame, usually you know your interface card, you know its source MAC address, right? But your interface card does not know the destination MAC address. So the problem is, how do we get the destination MAC address? So again, every node, every operating system, they should maintain an ARP table. ARP stands for Address Resolution Protocol. It should maintain some records about what is the IP and its corresponding MAC address, and the TTL. TTL stands for how long time to live. Okay, time. What is the expired time of this entry? Okay, but how do we how the operating system use ARP protocol to get the MAC address. So I'd like to show you right here. So supposedly A and B are two nodes in a subnet, okay? And A is 137.196.723. It's its IP address. And B is 714. Okay? So A and B knows IP address of each other. Okay? But A would like to know B's MAC address. So how do they do so? Let's take a look at this figure, okay? So basically, A will send a ARP query. It is a packet, okay? It is a packet. So at layer 3, it is quite simple, right? Because A knows its own IP address. So it writes 137.196.723. And also it knows B's destination address, which is 137.196.714. Okay, that's very, very simple. That's very simple. But right here, you can see that at layer 2, A, of course, it knows its MAC address is 71.65, so on and so forth. Okay, and right here, because A does not know B's MAC address, so it's very important right here. A simply just use FFFFF as the destination MAC address in this ARP query. That means I don't know what is the MAC address of B. I simply just broadcast this packet, this frame, to all the nodes in the subnet. And as we mentioned before, because the channel broadcasts this signal to all the other nodes, so B, C, and D will get this signal, no matter from Wi-Fi or from Ethernet. Okay, and for let's take for C. Okay, for C, after network interface card on C, it received the signal sent from A, and it will take a look at the frame, and it says, okay, this is from 71.65. Okay, this is from A. Okay, from certain network interface card, and the destination address is FFFF. That means a broadcast. So at layer 2, C will receive this frame, and further it will send this frame, it will unpack this frame. Okay, we'll unpack this frame, and it will see the message encapsulate in this frame, and it said, okay, it's an ARP packet, and it said it's from IP address 7.23, and it would like to know the destination address 7.14, but C is not 7.14, right? So C will drop this packet, because this packet is, although it is broadcasted, although C received this frame, but in this ARP packet, it is not for C, and it is not for D. But for B, after it received this signal, and let's take a look at the layer 2. Okay, this is the broadcast FFF, so it will unpack this ARP, this frame. And in this ARP packet, it says, okay, we'd like to know what is the MAC address of 7.14. And B says, okay, it's me. So, again, let's take a look at this one. And again, B will send a ARP reply back to this subnet. And take a look at it, the figure I draw. Okay, the MAC address will be 5823 blah blah blah, and the destination will be A's destination MAC address 71.68.65 and so on, blah blah blah. And the IP address is 7.14 to 7.23. It's from B to A. And again, this frame will be broadcasted in this Wi-Fi environment or in this Ethernet environment. So A, C, D, they all receive the signal sent from B. But C and D, after receive the signal, and they take a look at their two MAC address. Okay, let's say the destination address is 7165. So B says, okay, that is not my friend. So C and D will both drop this broadcast packet. And only A, receive this signal and take a look at the MAC address. Okay, the destination is 7165, it's me. And then we will unpack the packet and say, okay, that is our reply. And it says, okay, B's IP is 7.14, right? And its corresponding MAC address is 5823. And then A can write down this entry in its own ARP table. So that is how A get B's MAC address by using ARP protocol. Okay, that is not that difficult, but it is very, very straightforward. Okay. So after that, A, B, C will both learns how, both learns what is the MAC address and its corresponding, how A, B, C, D, they will all maintain its own ARP table, and they will send query to all the other nodes and to learn what is the MAC address of the corresponding IP address. Okay. The next is the last topic, is not related to the previous one. I would like to talk about how do we do routing. That is not related to ARP. Okay, make sure you understand that. So think about a very simple network. Okay, we have a network at the left hand side. Okay, we have a red interface card because they belong to the same subnet, and the right hand side is another subnet. We have 3. Maybe red is better. Okay, we can say that we have 2 subnet connected by 1 router, right? When A want to send a packet to B, okay, then how MAC address and IP address collaborate with each other to send a frame from A through R, which is a router, and then router will route it to B. Okay, that is the problem of. Okay, so first you have to know that A's IP address is 111.111.111.111, and B's address is 222.222. Okay, and for its router, as we mentioned before, because the router has multiple interfaces, and one is connected to the red one is connected to A, the green one is connected to B. So at the red interface card of the router, okay, it has an IP address is exactly the same subnet as A, and at the right hand side, it has another interfaces with another IP address, which is the same subnet with B, right? So that is, and of course we have different network interface card, and its ID is right here. Okay, so let's take a look at. I think this one is good enough. Okay, so when A want to send a packet to B, okay, it should be a frame, right? So as we mentioned before, the IP address, the source IP address is A, so it is 111, and its destination IP address is B, and it is 222. That is good. But how about the MAC address? So when A encapsulates the datagram and want to create a frame, this frame, its source MAC address, it should be A's IP MAC address. So it is 74292C, right? But one important thing is that what is the MAC destination address should be written in this frame. Could that be B's MAC address? The answer is no. Because when we talk about ARP protocol only can be used within a subnet, so that A cannot send a ARP query through the router to B. No, it is not possible. ARP packet can only exist in a subnet. Router will not forward or route the ARP packet to the other subnet. So A does not know B's MAC address if they are at two different subnets. Okay, so the only MAC address, destination MAC address, A can use is router's MAC address, which is right here. E6, E9 is right here. Right? Because A would like the router R to help A to do routing and forwarding. So A need to know R's read MAC address. So basically, again, A will send this frame out through a broadcast channel. So actually C's read card, interface card, and R's read interface card, they all receive this frame. But C will drop this frame because the MAC address, the destination MAC address is E6, E9. It is not C's MAC address. So C will drop this packet. But R's read packet will receive this frame and then take a look at the MAC address. Yes, it's for me. And then we'll unpack this frame and see, okay, that is from 1111 to 2222. And R will notice that, okay, I'm not 2222, but I'm a router. So this packet will goes out of this subnet to the right hand side, according to R's forwarding table. Right? So R will later encapsulate this diagram again, but right here you have to see these pages, okay? And then we'll pass the diagram to the right hand side, to the green interface card. And at that moment, we'll do encapsulate again. But the source IP address right here is this one, 1A. That is R's green interface. And what is the destination MAC address? That is 49BD. That is B's MAC address. So that every time when a router receives a packet to be routed from one subnet to the other, the router has to get this frame and unpack the frame and take a look at the destination IP address and check against with the forwarding table. And then the router will encapsulate the diagram again to a frame, and by using its own MAC address as a source address, and to the next step. In this example, it is B. Because R and B are in the same subnet, so R can use R port code to know what is the MAC address of B 2222. Okay? And I would like to draw something right here, okay? If it is more complex, for example, we have an A right here, and we have a router right here, and we have some other routers right here, and some routers right here. If it is more complex, okay, when we do routing, okay, we have several different routers in the route, right? Make sure you understand one thing, that when we talk about subnet, okay, that is a subnet, right? And that is a subnet, that is a subnet, that is a subnet, and that is another subnet. Okay, so every time when we pass the frame from one interface card to another interface card, it is good enough to use our protocol to understand, to know what exactly the MAC address of the source and destination, right? But when the router do routing, okay, actually it changes the frame, the source MAC address and destination MAC address. Okay, and again, when do routing, they all changes every time when it do the route. When they pass to another subnet, the router need to change the MAC source address and the MAC destination address. So in this example, 1, 2, 3, 4, 5, there are 5 different pairs of source MAC address and destination MAC address has been used in this specific route. But for the IP diagram, okay, the IP source is always 1111 and it's always 1111 to 2222. But the underlying MAC address changes every time when it passed to when we forward or pass to another subnet. Make sure you understand that. Okay. So it is the same. Okay. I use the same view graph to explain the things. Okay. So that is the MAC address. How do you use your MAC address to do routing? Okay, so and that's all. That's is the result. That is the content of MAC addressing.